This is electronics. This is circuit electronics. This is technically topic 4. The first 2 topics we've got to do with thermodynamics. We did one which was just thermodynamics and one which was more about climate change. Then we've done electronics, where we've just looked at electricity, modeling what is electricity, how does it work. Now we're going to look at actual circuits, and in the background here for a circuit. To start off our topic, I thought I would choose something relatively simple to talk about in just the one period. So I decided to, and then on Tuesday we might start moving through the heavy stuff. I thought I would start with Kirchoff's rules for current and voltage. And the idea is for these is we will learn how current and voltage are conserved. There's missing an S here. So we're going to look at how current is conserved and how voltage is conserved. Kirchoff discovered that these things could be conserved, and how we did that was pretty important. Let me just tell you how we did it. Gustav Kirchoff. Now, the reason I've done this slide is because, you know what, to be honest with you, I've seen the Kirchoff's rules so many times, and I've never actually thought about who was the guy that came up with them. So Gustav Kirchoff was born in Russia. I mean, back in his day, it was called Prussia, but still. And what he did was he did a couple of things. He helped discover cesium and rubidium, and he did that with the help of Robert Bunsen. And Robert Bunsen was well known for inventing the Bunsen burner. He helped develop spectroscopy, and he helped develop thermodynamics. And remember, we talked about a lot of time the black body radiation. He was one of the main people that sort of pointed out. Came up with the theory, yeah, all things above 0 degrees Kelvin must emit some kind of radiation. So he was the thing. But what he made was he made his own laws of circuits. And the main idea that I wanted to start off with, we're going to talk about 2 laws that he came up with. He came with other laws for other things, but he came with 2 laws for circuits. The first law is essentially, he said, pretty much we can break it down into something simple. The current going into a junction is equal to the current going out. The current going into a junction must equal the current leaving. Essentially, if you think about that, it sort of makes sense. If you've got a river that's running, and then it splits off into 2 rivers, you can't just lose that flow. That flow doesn't go anywhere. It must split. And it must go some of it this way and some of it this way. And what Kirchoff said is, like, if you know how much goes up, then you can use that to figure out how much goes down, because you must know the amount that goes into a junction must be the same as what goes out of a junction. We're going to do some examples now. These examples are pretty easy, but let's just do them anyway. We've got 20 amps going into this junction and 30 amps also going into the junction. We've got X amps coming out. Well, if I've got 20 plus 30 going in, that must mean that's equal to the X going out, which means that X must be 50. We must have 50 amps leaving this circuit. Pretty simple. The second one, and we know this is conserved because, again, we know that the current can't just disappear. We can't just lose current. Remember, current is a charge per second. So we have to be able to account for all the charge. The charge needs to be conserved. You can't just lose charge randomly because 2 wires connect with each other. Let's grab a look at this guy here. We've got 3 going in and 2 going out. Going in, we have 25 plus 10 plus X. Coming out, we have 45 plus 5. That's going to give us 35 plus X equals 50. which means that X is what? What is X going to be? I'm going to check that you're paying attention.
15.
X is 15. Correct. So this is Kirchhoff's first rule. Now, you guys might be looking at this sort of stuff. Maybe you're thinking to yourself, okay, yeah, this is easy. This makes sense. I originally, when I first saw these problems, thought, what does this have to do with circuits? These are, yeah, I can see maybe it'd be useful, but these are just random wires. It wasn't until I started to look at circuits like this. Let's actually draw a circuit. Rather than drawing these, let's draw a circuit. What would it look like? Well, let's take this circuit here. This is a beast of a circuit. This has got a lot of things. We've got a battery over here. We've got some wires going over here. We've got a junction here, a junction here, a junction here. And these guys at the top and the bottom, these are resistors. This is how I'm going to draw our resistors as little boxes, just because mostly in Word it's pretty easy. Now, let's grab a look at this very, very first junction. At this first junction, we have going into it, we have 50 amps. Going out, we have 10 amps, 20 amps, and something that's not written here. Well, we can work that out. 50 going in equals 20 plus 10 going out plus X going out. X is going to be what? Someone? What's X going to be? What is our current going upwards going to be? Someone has said in chat, 20. You are right, Lucius. That is 20 amps going up. Perfect. Why is it 20? Because 20 plus 10 plus 20 makes 50. Let's go have a look at this junction here. So we've got this 10 amps, yeah? That 10 amps is going to come into a new junction. We've got 6 going down, and we've got another value going to the right. How much is going to the right at this point? Someone said it was 4. You are right, Brendan. It is 4. 10 plus 6 makes 4, which means that going into this junction, we have 4 amps. We also have 20. So coming out the other side of this junction, how much are we going to have coming out here? Who said it this time? That was a 24 from Vu. Oh, haven't seen you give an answer today. Yes, 24 is correct, Vu. 24 amps comes out. Now this 24 amps is going to come down, going to come across until it hits here. And at this point, that 24 amps is going to come in contact with the 6 amps from the other side of the resistor. 24 plus 6 is going to give us 1. Oh no. Let me see. That was 24 to 30. Yep, you're right. You are. It's going to be 30. 24 plus 6 is going to give us 30. I need a new color. And then that 30 is going to come in contact with this Y here, which had 20 in it, and 30 plus 20 is going to leave us off with what grand total at the end? What are we going to have at the very end of our circuit? Actually, probably shouldn't use yellow. 20 plus 30 is, thank you, ladies and gents, 50. Thanks, Brendan. 50. Our last bit is 50. We have 50 amps at the end, and that is the current that goes back into the battery. And if we look, 50 amps at the end, 50 amps at the start. The flow may split. but ultimately it all comes back together at the end. And that's his first law, and that's how we can use this. Later on, what we're going to do is we're going to use this shortcut a lot of times. Sometimes I've found students do complicated versions of calculating resistances and stuff just to find the current, when you could just go, oh, well, it has to be 20 minus 20, 50 minus 20. This is a way more complex example than these examples that we started off with, but it's the same principle. If you know that the current is going from the left to the right, in this case it's going this way, you got 10, that has to split into 6 and 4, because that makes 10. This, I could have just drawn that little bit there, just like this. And if I had done that on the previous page, it'd be a lot faster for you guys to do. So current splits, okay? Current can split, but we have to make sure that if it does split, what goes in equals what goes out. That's Kirchoff's first law. His second law is not about current. His second law is about voltage. Kirchoff's second rule: if any closed loop, and we're going to talk about what this means a little bit today, but also a lot more later on. If any closed loop in an electric circuit, the sum of the voltage drops is in that circuit in that loop must equal the sum of the EMF. So the amount of batteries. But in other words, how I like to usually do this, by the end of the circuit, the current should have 0 volts. You should have no energy left. And the answer I usually give to that is, why would electrons have any energy left when they reach the positive terminal of the battery? When they get to the end, that's where they want to go. So they don't have any energy to want to keep moving forward because that's where they want to be. Let me show you an example of how, let me show you 3 examples actually of how this rule works. And then I'm pretty much done for this lesson. The first one is this. We've got a battery over here. Now this battery has 20 volts. Yep, I'm happy with that. That 20 volts is going to go through this is a circuit, which means that the sum of the voltage, the sum of the EMF, 20 volts, must equal the sum of the voltage drops. So how much voltage is going to get dropped over this resistor? 20 volts. 20 volts gets dropped over that resistor because that's what there is in the circuit. What about this guy here? Whoa, what have we done differently? Now we've got 2 resistors. Okay. Now, if I was to say, all right, well, let's do the same rule. -20, -20. Now it doesn't work because now the voltage drops are negative. The voltage drops are -40, whereas the voltage from the power supply is 20. That doesn't work. So what I do to fix this is I change it. Instead of making this one -20, I'm going to make this -10. And I'm going to make this one -10 because then they're both equal. Now that, because I've got 2 resistors and they're dropping voltage to dropping resistance, that might mean the current is lower. We don't care about the current at the moment. We just care about the voltage. The 20 volts in, 20 volts out. Everyone's happy. Let's look at one more example. This one's a little bit more challenging. Now, the question says, the statement says, in any closed loop. Now, I told you I would explain what that would mean. Oh, by the way, this part here, where it says the sum of the voltages, that means if I take -10 plus -10, that's going to equal -20. That's what the sum part means. But in any loop, this is a bit interesting. In this circuit on the left, there are 2 closed loops. Here is one closed loop. And here is a second closed loop. And in both of those closed loop, we have to lose 20 volts. Now in the red one, there's only one place to lose 20 volts, and that's over this resistor. So this resistor drops 20 volts. But in this other one on the outside, we've got two resistors. And because we've got two resistors, we have to lose 20 volts in total. If those resistors are the same, which I'm going to tell you for this example, they are the same resistance, then they will both lose 10 volts. Because 10 plus 10 is going to mean that's going to lose 20 volts. And the red line is going to lose 20 volts. What's interesting about this is that even though these are the same size resistors, because this is on its own loop, right? Because this is on its own loop, it drops 20 volts, whereas these ones share a loop, so they drop 10 volts. I should point out that this becomes even weirder when you start to deal with situations where you might have this going on. That would be a bit of a challenge, this one, because in this scenario, right, in this scenario, you've got two loops, but this resistor, you've got one loop here and one loop here. But why this is a bit weird is that resistor is in both loops. So that means you would have to be careful about how much voltage that's going to lose. Because essentially that's going to lose, essentially that in that case, I think would be, if this was 20 volts, then that would be 10 minus 10 minus 10 minus 10. Because when it's part of the blue loop, it has to lose 10 volts, because 10 volts makes 20. When it's part of the red loop, it needs to lose 10 volts, because it needs to be part of that loop. It's a bit, this one's a bit of a weird one, but yeah, that's how you would do it. And you're going to get odd ones like these, but these are just 3 examples. So those are Kirchhoff's rules. The first rule, I in equals I out. The second rule essentially is, you know, each loop must drop all voltage. There's different ways you could say it, but that's the fastest way that I think I can say it. Got like about 5 minutes left. So in this last bit, what I want you guys to do after this is I want you maybe to start, and I'm not going to make this due today. I'm not even going to make it due on Monday. I think I might make this due Tuesday to give you guys a chance to work on this. But 4.2 doesn't have that many questions in it. And so that's what I'm going to get you guys to work on afterwards. 4.2, for the record, looks like, let me see if I can find it. This guy here is near 4.2. Yeah, this is the next bit. So 4.2 has a lot of problems that look difficult, but they're not too bad. So this one here, I can put these questions on Classroom, but obviously I can't do this right now because I'm in the middle of the lesson. You have to wait till after school, after 3 o'clock, because I've got one lesson after you guys. This one here, if I've got 4.8 volts being used here, and I've got 12 volts as the total, then I need to work out, well, I need to make sure that I get to 0 by the end. So 12 minus 4.8 That's going to give us, oh, I can't do this in my head. 7.2. Wow, thank you. Someone that can do it in their head. 7.2. I think that looks about right. 7.2 volts. So that means this here is going to be 7.2 volts. It needs to be that because ultimately 4.8 plus 4.8 plus 7.2 equals 12 volts. That's the voltage that's in the circuit, and that makes up a loop. It does get a little bit more challenging later on. I found that like there were in this question here, question 3, it's a little bit more challenging, but ultimately, you know, you're still doing the same stuff. 24 volts. If you know this is 8 volts, then here's one circuit. Here's one loop. So this loop needs to drop 24 volts. If they've got 8 volts that dropped here, that'll give you an idea of how much might be dropped here. But there are 2 loops in this. There's one loop, there's another loop here. And this part is still dropping 8 volts, so that should give you an idea of how much might get dropped over there. I'm not going to tell you the answer to that one, I'll let you figure it out. Then these two are 2 examples very similar to what we did before. I'm looking at this thinking it should take you like maybe 2 minutes to do this exercise. Some of the examples here, this is a very similar one to what I just did before. And then even this one with current, very, very similar. Remember, if you've got 11.1 amps going in, that must be split. So you've got 3 amps here, 5.7 amps here. What must be going down the middle? Well, 3 plus 5.7 is 8.7. 8.7 plus, I think, 2.4 or 3.4 will give you what B is. And then that comes out and then it goes back around. So, and then they all combine here. So just keep that in mind to work out what needs to go where. So that's going to be it for today's lesson. Yeah, thank you for listening. And yeah, I'll see you next time.